Today got a quick, interesting, free resource for learning physics. You can go on Google and search up the Feynman Lectures on Physics. First link is going to get you to this page. This is the website, feynmanlectures.caltech.edu. Right here we got Mr. Richard Feynman. Here's a picture of him right here with some of his boys. And he was a professor and a physicist sometime in the 1900s. And he made all of his lectures available online for free. You can also get hardcovers of these books. They're expensive, but it's cool that everything here is free online. So we got 3 volumes, mainly mechanics, radiation, and heat, electromagnetism and matter, and our interest today is quantum mechanics, which is all of volume 3. Feel free to explore this at your own will. Feynman's tips on physics. There's some other stuff in this website here, so you could take a look at that. But let's just dive into volume 3 over here. So you can see how it's organized, the Feynman Lectures on Physics, Volume 3, Quantum Mechanics. It was also written by Leighton and Sands, so these 3 people together. I'm not too sure who Leighton and Sands are. Kind of sad, maybe I should educate myself. But I know Feynman. Feynman did a lot of cool videos on YouTube you could check out. Richard Feynman Fire, he explains fire in a really interesting way. He also talks about like studying physics in general and how you don't have to be born like a super genius. He keeps saying like, I was just a regular kid and then I worked really hard and I studied physics and then I got better. I kind of doubt him a little bit because I saw some stories of him doing like advanced calculus on manifolds and shit like this when he was 12 or something crazy like this, so take it with a grain of salt or a grain of sand. But anyway, here are his lectures. They're amazing, very well written. They could be a little dense. You click expand all and collapse all. Let's do collapse all and just see the chapters in general. So it starts with about the author's preface to the new edition, Feynman's preface forward. Chapter 1, quantum behavior. I remember when I was interested in quantum mechanics, I started reading this. It talks about the double slit experiment. So an experiment with bullets, the double slit experiment with bullets, double slit experiment with waves and with electrons, interference of waves, stuff like this. I read this so many times and I was like, man, I'm not getting anything in my head. But then I jumped to chapter 2 and I read this quite recently, and it did a great job of explaining the uncertainty principle. It starts with probability wave amplitudes and goes on to talk about some interesting stuff, the size of the atom, crystal diffraction. It's a non-traditional curriculum. So this is not the same kind of order that Griffiths introduces things in. Griffiths starts with the general like bird's eye view of quantum mechanics, like the wave function, the Schrödinger equation, the uncertainty principle, stuff like this. And then he dives into a bunch of examples. But Feynman kind of hits it a little bit more of an experimentalist route. So he gives you a lot of like tangible experiments. And this is great because quantum mechanics, sometimes it's like very ethereal. You don't really know what the wave function is. You have no clue what's happening. But this guy gives you a bunch of experiments and a bunch of real world applications of quantum mechanics, which could be kind of useful. So I read this thing here. I'm not going to read it on the channel unless you guys want me to, because it's just reading, could kind of bore some people. Today I just want to show you that it's a possible resource for you guys to get a different vantage point of quantum mechanics. It's going to be super helpful. So we have probability amplitudes, identical particles, spin 1, spin 1/2. Spin is a pretty advanced topic in quantum mechanics. I think with Griffiths you learn it near the end of chapter 4. Chapter 7, the dependence of amplitudes on time. The Hamiltonian matrix. So you can see how quantum mechanics is related to linear algebra and matrices. The ammonia maser. I have no idea what this means. Let's actually take a look. The states of an ammonia molecule, the molecule in a static electric field, transitions in time-dependent field, transitions at resonance, transitions off resonance, the absorption of light. Ah, cool. Maybe the photoelectric effect. Anyway, we got other two-state systems, more two-state systems, the hyperfine splitting of hydrogen. This is super interesting. You can get into it if you're interested. Propagation in a crystal lattice, semiconductors. Really cool. Every electrical device has semiconductors in it. Semiconductors are super interesting and strange. So you could read about them here. Let's take a look. Electrons and holes in semiconductors. You learn about holes, which is literally the absence of electrons, but you treat them like actual things, like positively charged things. Impure semiconductors, the Hall effect. Semiconductor junctions, rectification at a semiconductor junction, the transistor. So this transistor is the thing that's in every electronic device, and it's made with several combinations of semiconductors, a junction of semiconductors. We got the independent particle approximation, the dependence of amplitudes on position. So this is related to the dependence of amplitudes on time. Pretty cool. Symmetry and conservation laws, angular momentum. Angular momentum has always confused me. It's very, very deep. It gets related to this kind of math called groups, and angular momentum is represented by this specific group. I think it's SU2 or something like this. Don't quote me, I'm not a fantastic mathematician. The hydrogen atom and the periodic table. This is talked about in Griffiths, so maybe you can dive in here and take a look at what is going on. The Schrödinger equation for the hydrogen atom. Look at this. So chapter 4 Griffiths, you could just dive into here and see what it is. You know what, as an example, let's just check the last two chapters quickly. Operators, the Schrödinger equation in a classical context, a seminar on superconductivity. So let's just dive into one of these. I'm going to click here, and you can see how it's organized. It's actually very cool. Over here on the side, you can increase the font size. So here they just have a standard like picture from his blackboard when he did the teachings, and then it's broken down into each of the sections. If you click here, you can go to all of the sections. If you click here, I don't know what happens. This is night mode. Look at that, that's clean. You can also change the font size. Beautiful. You can navigate different sections, social media, but there is something really interesting here, which is this little original lecture recording. If you click on this, you get this thing here. Let's see if my audio will pick it up. So the guy actually did recordings of his lectures in the classroom, and he put them here. It's kind of similar to this. I think the writings are a little bit more updated, but if you want to listen to something, you can just pop this on, listen to it while you're walking a dog or something, or in the car. Pretty cool, pretty original kind of lecture. Most of the things that you're going to hear here have not changed. Quantum mechanics has been pretty stable, at least the type of quantum mechanics we're learning. So yeah, explore all of this stuff here. Let's just take a look how it's looking here. We got some beautiful equations. Schrödinger equation right here. They expand the Hamiltonian operator. This is for the hydrogen atom, remember. So we have the hydrogen atom potential, all right? Taking v equals 0 at large distances from a proton, we can write, boom, potential energy of the electron in an electrostatic field of the proton. So this is the potential energy of the electron in the hydrogen atom. You plug this into the Schrödinger equation, you get this modified equation. We want to look for definite energy states, so we try to find solutions that have the form, boom. Why do you pick this? Don't stress about it. The function psi must then have a solution, boom. So maybe he skips a little bit over the math and he kind of just shows you the final results. But yeah, a bunch of interesting equations that you can look at here. This equation, I believe, is called the radial equation. And then later we should get the angular equation. Angular equation should be somewhere here. Maybe he just like works on the radial equation first. He gets some values, like the energies. The angular equation gives you some kind of angular information. Let's see. Okay, here we go. This theta and this phi are two angular components, the azimuthal and the something else. Here you see a different form of quantum mechanics with the Brockhead notation, the Dirac notation, I believe. And yeah, he expands a little bit this little y functional, or whatever it's called, the angle functions. This is the same thing you're going to see in Griffiths. So nice little like supplementary resource that you could read in adjacent. Here's a little table. Aha, here we get something that looks familiar from chemistry classes maybe. Here we get the final wave function of the hydrogen atom, I believe. This to me looks like the angular equation. A bunch of angles, a bunch of thetas and phis. Let's just see what his final results are. It's a pretty thick chapter. The hydrogen wave functions. Here we go. This is very interesting. So from quantum mechanics, you can figure this stuff out here. And this actually matches with experiment, if I'm not mistaken. These little energy levels. Nice. The periodic table. Very cool. Aha. Here we got some elements. How people develop the periodic table, I'm not sure. And a lot of writing. So if you're interested, read some of this. This is where the thing ends. If you click up here, you go back to the original section. And, you don't have to read all of this. It is very dense. Like I said, I was reading chapter 1 like 5 times, did not understand anything. Then I moved to chapter 2 and I learned something cool about waves and the uncertainty principle, and how the uncertainty principle actually isn't solely something in quantum mechanics. The same thing exists in wave mechanics, which existed long before quantum mechanics. So when you hear about the Heisenberg's uncertainty principle, you instantly think of quantum mechanics, but it's a little bit older than that. So pretty cool. And it shows kind of a relationship between wave mechanics and quantum mechanics. So that is all I have to share with you guys today. The Feynman Lectures on physics. Take a look at this guy, very cool, and take a look at some of his videos online if you're interested. This is free, so feel free to use it. And let me know if you have any questions about these lectures. Let me know if you have a favorite section or chapter, something interesting you found. Maybe I'll take a look at it too. Thank you guys for watching. See you in the next video.